All right, hi everyone. So in this talk, I want to go over some Python tools for analyzing the Ocean Observatories Initiative hydrophone data. So the Ocean Observatories Initiative is a large ocean observatory that has a large suite of different oceanographic sensors, and part of that are 11 different hydrophones that are constantly recording the ambient soundscape. So one of the main things I want to talk about today is using the Python package ooipy, which will kind of go over how to download data from the OOI hydrophones and then play around with it a little. So in this notebook, I've included some instructions on how to set up your Python environment for this notebook and to download all of the dependencies. So if you're following along at home or if you want to be able to run this code on your computer, these instructions will help you get that set up. But I'm going to skip over that for now. So it's in the notebook if you're interested. And we'll start by talking about ooipy. ooipy is this Python package that myself and several other people from the University of Washington have created to sort of stand in as an API for the OOI hydrophone data. Because a lot of the sensors in OOI are accessible through the OOI supported Data Explorer, which is a really great way to download and access the data. But the hydrophone data isn't. And so this sort of is hopefully a stand-in and it can download and access the data, calibrate the data, and compute things like power spectral densities and spectrograms. So I wanted to quickly point to the documentation here. The user guide here is very similar to the tutorial that I'll give today. But if you're interested in this Python package, seems like it would be interesting. This resource exists to try to help you get up to speed on it. So I mentioned there's 11 different hydrophones that are part of the OOI cabled observatory. And so if I scroll down here, it shows the 11 different hydrophones that you can download with the ooipy package. And if I open this link, it'll show a map of the different hydrophones. So you can see they're in various different places in the ocean. Some of them are on top of seamounts, like these two here. Several are bottom mounted in the deep ocean, and then on various different locations up the continental slope or on the continental shelf. So it's a really great resource to have open access ambient sound data and to do research with that. Okay, so let's get into the code and start playing around with this. So I'm going to import some packages here, and then we're going to just use this get acoustic data function that's part of ooipy. So you have your start time, you define your end time. So we're going to look at I think, 2 minutes of hydrophone data. And we're going to look at the node LJ01C, which is the Oregon offshore hydrophone. So I believe it's this one right here. So we're on the continental slope. It's at a depth of about 600 meters. So if I run this, it's going to go off to the raw data server where all of the hydrophone data is stored, figure out which files to download, and then stitch them all together into a single hydrophone data object. So this HData is the hydrophone data object. And we go into more detail in the documentation, but this object is a wrapper to the obspy trace object. And so you have all of the functionality that the obspy trace object has. So basically this object has the metadata. So you have the start time, end time, number of points, the sampling rate, and all of the processing that's been done. And then it also has a NumPy array with this data. So there's lots of different methods that come with this object. So if I kind of scroll through these, a lot of these are from the obspy trace method. So in obspy, you can filter, decimate, detrend, you can do kind of all sorts of things. And you can see more about that in the obspy documentation. But you can, for instance, I have here, you can just call to plot it and it'll plot the time series of the data. You can kind of see what the contents are. This is 2 minutes of acoustic data. So part of the ooipy hydrophone data object is that we have several methods that are specific to the OOI hydrophone data. And one of those is to compute the power spectral density. And this actually, there's lots of different inputs that you can use. You can specify how you want to do it. It's going to use the Welsh method, but you can specify the window that you want, the number of points per FFT, how you're averaging, and so on. So if I compute this, it will give us a calibrated power spectral density estimate over this 2 minutes. And that's going to return an X-array data array. And we'll talk a little bit more about that later in this tutorial. But we can plot this PSD and we can see what the power spectral density looks like for this 2-minute ambient sound segment. We can also listen to the data. So here I'm just going to remove the mean and divide by the maximum so it's easier to listen to it. And then we will, let's listen to a 15-second segment. So conveniently, our little time segment happened to have a humpback whale calling, so that's cool. So we can also take this time series that has the humpback whale song, and we can calculate the spectrogram. So this compute spectrogram method, it's actually estimating the power spectral density as a function of time. So it's not a typical short time Fourier transform. And so we don't have the phase information as well. But you can specify the averaging time and then the number of FFT points that you want to use. So here, if we run this, we get this same X-array data object. So it's a two-dimensional array with a time and frequency coordinates. And then we can plot this data and see this vocalization. So I can zoom in here on the maybe first 6,000 hertz, and we can see these individual humpback whale calls in the spectrogram. Another function, another method that we have in the OOI hydrophone data object is the ability to save this data. We have several different output types that are supported. You can save it as a pickle file, which just pickles the full hydrophone data object. You can also save it as a netcdf file, which is one of the standard file formats for geospatial data. You can save it as a mat file if you're interested in doing analysis in MATLAB. And you can also save it as a WAV file if you want to listen to the data. So here I'm just going to save it as the file name as humpback, and then we'll save that as a mat file. And so you can see here, this showed up, and you could open this now in MATLAB if you wanted and do processing in MATLAB. Another thing that we have with ooipy, which is the ability to do batch downloading of acoustic data. So there's a program that comes with ooipy when you install it with pip called download hydrophone data. So if I type download hydrophone data -h, this will give me how to use this program. So basically you supply it a CSV file, and then you give it the output path that you want it to save the files for. So I have an example CSV file that is in the repository that you should see as well. And it specifies 3 different files that we want to download. So we're going to look at this same time frame where the humpback whale is singing, and we're going to download 3 different 1-minute sections from this same hydrophone location. We'll download it as a WAV format so that we can listen to it. So I have this CSV. So now if I run this program, download hydrophone data, I supply it the path to the CSV. And then the path that I want to save it to, I'll just use the current working directory. So that's this dot here just means that it will use the current working directory. So if I run this program, it'll calculate, this will be about 90 megabytes of data. Do I want to download that? Yes. So then it'll go off and it'll download these data segments and convert it to a WAV file where we can listen to it. If we go over to the files, you can see that they're going to come in. There's the next one. And these are just WAV files so we can listen to them. A little more of the song there. Okay, so yeah, you can kind of set this up. You can create your own custom files that you want. If you wanted to download a lot of data, you can set up this batch downloading. Okay, so that's a little bit about ooipy. And if you're interested in this or you think that this could really be useful in your research, I'd really encourage you to check out the GitHub. Um, if something isn't working, you can submit an issue. And I also want to heavily encourage community involvement. If you have a feature that you'd like, I would love it if you tried to create that feature in Python and submit a pull request. So if you're interested in this code, I would definitely encourage you to check it out and to consider collaborating on it. So now I want to change topics just a little and use some data that I pulled down already and downloaded with ooipy. And we're going to play around with some Python packages that allow you to scale your processing up to be able to handle big data. So it can do larger than memory calculations, and it can also distribute the computations to however many cores you have. So I want to talk about a couple of Python packages, and one of the main ones I want to talk about is Xarray, which is a really great Python package tool that fits into the scientific Python data processing framework. So one of the goals for this talk, I want to just demonstrate some of the capabilities of these Python packages, both Xarray and Dask. So in this talk, I'm not going to be able to really go into the details of how to fully utilize these tools, but I wanted to demonstrate what's possible. And then if it seems like it could be useful for your research, I would really heavily recommend checking out this book, which I think does a great job of describing it in more detail. So this book goes over data science that's specifically for Earth and environmental data science, but I think it applies really well to acoustics. And there's a chapter about Xarray that I put a link to in the notebook. So if you're interested in Xarray and you want to get a better and more in-depth understanding of what it is, I'd really heavily recommend this website and this book chapter. But the basic idea of Xarray, and I have it in this picture here, is that it combines the concept of an n-dimensional array, like we're familiar with a NumPy array or a MATLAB matrix. And it combines the n-dimensional array with the idea of adding coordinate vectors as well. So you can imagine if we have a two-dimensional spectrogram, we have a time dimension and a frequency dimension. And the values of that two-dimensional array are the spectral levels. But then you can also, Xarray allows you to supply a vector of the time bin values and a vector of the frequency bin values. And it kind of tracks and keeps tracks of the units of the array as well. And Xarray also has lots of different methods that allow you to do distributed computing and larger than memory computing. So I wanted to play around with some big-ish data. And so I have this 1.5 gigabyte data set that you can access at this link here. And if you're following along, you can download this and put it into the same directory. You'll need to unzip it, and then you'll have a file called lf_specs.zar. So there's one other Python package I wanted to mention, which is Dask. And it's going to be a backend to Xarray, so we're not actually going to have to work with it. But it basically allows for you to distribute your computing to multiple cores. And it does this thing called lazy loading and lazy computation. When you open a data set, it doesn't actually pull the data into your memory. It just has a pointer to where that data is stored. So I can kind of show that here. I open up this data set and it is backed by Dask arrays. And it's a big data set. This is the full 1.5 gigabyte data set. But it's not actually pulled into memory. It's just these pointers. And then you can do computations. You can write a computation like maybe I want the absolute value of this data set. It doesn't actually compute it. It just creates a recipe of how it will compute it. And then when you want it to compute, then it will send it to all of the cores. Dask also supplies this thing called a dashboard, which will allow you to see your different cores working when it's computing. Okay, so I have this data set of spectrograms for 6 years of data from 2015 through 2020. And I have it for the 5 different low frequency hydrophones that are part of the OOI cabled array. So you can see each individual data variable has a large array has 257 frequency bins and then almost 200,000 time bins. And that this full array is about a third of a gigabyte. So we can visualize the spectrogram using a Python package called hvplot. So I'm going to call just a single one of these variables and then plot this third of a gigabyte spectrogram. And you can see now it's going to send it off to the cores. I'm actually asking for the data. And so it computes the spectrogram and it re-rasterizes it. Since it's 200,000 pixels wide, it's going to do some downsampling and averaging so that you can visualize it. And so here's the spectrogram. This shows us frequency in hertz and time over 6 years. And you can really clearly see the seasonal finwheel vocalizations that are coming in at 20 hertz. So I can zoom in and it will automatically update the resolution and time where we can see individual ships passing by. So now you can see we're looking at several days. So that kind of shows you how we can use all of these different tools with Xarray and Dask to view the data. So now that we've looked at the spectrogram data, I want to do 2 little exercises with this spectrogram to look at how the statistics of the spectral energy change over frequency and time. So the first thing that I want to do is to compute the frequency quantiles. So there's this function in Xarray called quantile, which will let you compute the percentiles for the data. And so I'm going to compute the power spectral density percentiles over time for the 10th percentile all the way up to the 90th percentile. And so I'm going to compute these. And like I mentioned before, this is lazily computed. So I have this data set, I have the quantile values from 10% up to 90%. And then I have these arrays that are pointing to the actual data, and it has a recipe that it's built in these graph layers, but it hasn't actually computed anything yet. But now when I call the compute method, then it will send it off to the available cores, which I'm just using a laptop, so there's just a few cores here. But this same code can scale to supercomputers or cloud clusters if you're dealing with bigger data. So I can call compute, and it will send that off to the cores, and you can see how it's computing that. And then we can see what the percentiles of the spectral level look like over these 6 years. So you can see, so it's kind of color shaded. The darkest color is the 10 percentile, the quietest 10% of sound. And then the lightest color is the loudest 90th percentile of sound. So you can see that typically there's a span of maybe about 15 dB in most of the band, but you can really see the seasonality of the finwheel calls, where in the quietest 10% of the spectral levels, there aren't any finwheel calls. And then as we move higher and higher in the percentiles, the finwheel calls become much more prevalent. So the other thing I wanted to play with here was to look at the frequency bands and integrate over a specific frequency band. So if I go back up to the spectrogram, if we just integrate over some specified frequency band, we can plot the time series of that and see how it changes over time. So here I'm going to just convert this data set from dB back into linear so that we're integrating in linear space. Then I'm going to select only the slice of the frequency values that I want. So I'm either going to look at between 15 and 25 hertz or between 50 and 60 hertz. And then I'm going to integrate this data over frequency. And this just numerically integrates the array using the TRAPC method. So I set up the recipes. And then if I want to look at one of these, so this is the finwheel call. Let's look at a single location. And then I can plot this. And you can see there's quite a lot of variance because it's a 15-minute time bin. But maybe we wanted to re-sample this and we wanted to look at the mean and the standard deviation of this time signal for a monthly average timescale. So here we can do that with this code in Xarray really easily. We can resample it to be monthly, and then we can calculate the monthly mean and standard deviation for these different frequency bands. So then it sends it off to the cores and it computes these data products. And now we have the frequency band monthly mean and monthly standard deviation. And if I plot these, you can see how the 20 hertz band is different for different locations. And then if we wanted to compare for a single location, we could see how the 20 hertz band and the 50 hertz band are different with time. We can plot that here. So this is the central caldera location. The blue line is the 20 hertz frequency band, and then the orange line is the 50 hertz frequency band. So yeah, hopefully that gives you a kind of a starting place on what's possible with some of the Python packages for scientific computing, and also introduces you to ooipy and enables you to be able to use OOI hydrophone data for your research. So yeah, thanks for listening, and I'm happy to talk more during the panel.